For this lesson and the beginning of our next unit, we're going to be taking a look at what are known as higher order derivatives. And in particular, we're going to be tying those into three concepts that are fairly familiar to us in our day-to-day life. Certainly the position and velocity relationship is one that people are familiar with. And then acceleration, if you have any background in physics, all three of these and the relationship between them will be familiar to you. But we're going to be looking at them from the view of calculus and the idea of rate of change. So first of all, let's forget about any particular quantities and just take a look at this idea of higher order derivatives. So if we start off with some function, or if we're doing some sort of graph and it's just y equals f of x, then the first derivative, which is what we've been looking at so far, is dy by dx, the rate of change of y with respect to x, which we've also denoted in a short form as y prime, which we could also denote as f prime of x. So two of these are the prime notation, and dy by dx is the Leibniz notation. We haven't really talked about or looked at the idea of taking the derivative of the derivative again, but that's perfectly reasonable. And that's known as the second derivative. So when we start off with the original function and take the derivative, that's the first time we are taking the derivative. But we can actually take the derivative as many times as we like, so long as, of course, so long as the function itself and its derivatives continue to be differentiable, so long as we are allowed to take the derivative, then we can keep applying this. The notation for this one, the prime notation is actually the easier one. Because all that means is that you count up the number of little prime dashes or hash marks up here, and that tells you first derivative, second derivative. But the Leibniz notation is not so bad either. This actually goes back to when we talked about something like, for example, first differences. If we look at delta y over delta x, if we look at something like slope, or when we talked just about the first differences, well, when we talked about the second differences, we would sometimes use that notation, delta squared y. And the second differences were with respect to a single delta x. So all we're doing now is something more like this, delta squared y over delta squared x, which is we're taking the slope of the original slope. But of course, we don't want to do that in a very coarse way. We want to do that in a very precise way. So we want the deltas to become smaller and smaller. And so we end up with these d's. These d's are just like deltas. It's just the understanding is these d's are infinitesimally small. This is a tiny change in y over a tiny change in x. Okay, let's get a little more specific now with regards to position, velocity, and acceleration. And it is very important to understand that we are going to be working in one dimension. And I'm going to talk about that on the next page as well in a little more detail. So first of all, position is usually measured as the distance from the origin. And position includes a direction. So that means it's going to have a positive or a negative value. The two notations you're going to commonly see, it's not to say there couldn't be others, but the common ones you're going to see are going to be s of t or h of t. And what that's saying is that the position is a function of time. As time moves forward, the position will change. Now, when your position is changing, if you think about, for example, you're sitting in a vehicle, if you're sitting in the vehicle and it's sitting still, your position is not changing. And that means that your speed or your velocity is zero. If, however, you start moving, then you're no longer going to be in the same place. So velocity is the rate of change of position. Velocity tells you how is your position changing. Now this word velocity, this word position, all of these have the idea of direction built into them. Now, we're going to talk about direction only in terms of positive and negative values. So for those of you with a physics background, you're going to find this a little on the lighter side in some respects, but the introduction of calculus will be new regardless. So velocity is the rate of change of position. So if position is s of t, then velocity is s prime of t, or ds by dt. Acceleration is the rate of change of velocity. How quickly is the velocity changing? If you again imagine a car where someone presses on the gas very lightly, then the car is going to speed up very slowly. It's going to speed up, but it's going to speed up very slowly. So that would be a low acceleration. The rate of change of velocity would be very low. On the other hand, if you're in the car, and hopefully this isn't the case, where someone steps on the gas very firmly, then the car is going to accelerate quite rapidly. That's going to be a high rate of change of velocity. So acceleration is equal to v prime of t, which is also s double prime of t. So it's the first derivative of velocity, which is the second derivative of position. We could also use Leibniz notation, d2s by dt squared, and I actually could have included dv by dt for Leibniz notation as well, the rate of change of velocity with respect to time. So just a little bit more discussion about that. So because we're working in a single dimension, generally that's going to be up and down. If we're talking about the height, for example, an object being thrown into the air or dropped off of a building. Left and right, you might have to apply this in other situations. You might be dealing with something like a north or a south or east-west, something like that. But we'll only be working in a single dimension at one time. If you've come with a physics background to this, you're more comfortable working in two dimensions, working in north, south, east, west all at the same time. But for the calculus that we're looking at, it does work for two dimensions or even more than two dimensions, but we're not going to be looking at that. So the way we deal with that is the idea of direction is handled through the use of positive and negative. We assume one direction is positive, and usually it's a fairly intuitive choice. So we might choose up to be positive, which would make down negative, or right to be positive, which would make left negative, north to be positive, make south negative. Sometimes you'll have the choice, other times you'll have to read the question. The question itself might actually have specified it. They may specify it explicitly, meaning they may actually say up is positive, or it may be implicit in the sense that the text, or more specifically an equation, might actually tell you what the positive direction is. So here's an example of an equation. This is an equation that describes the height of an object being thrown into the air. And in this case, the important thing we want to look at is the initial condition. There are actually a couple things to look at here, but the easiest one is the initial condition. If we're throwing something into the air, if we're standing on the ground, then here we have an initial height of 2. And that, of course, is going to be above the ground, unless the question is quite specific and tells you that you're below the ground for some reason, throwing out of a hole or out of a pit. So if we are 2 meters above the ground here, that means that we're 2 meters in the positive direction, and so from this I can already conclude that up is positive. And that's a pretty safe assumption. I'm not suggesting you should make that assumption, but if you make that assumption, you probably won't go wrong most of the time, but it's always worth it to take a look at things. Okay, enough preamble, enough talking about that. Let's take a look at some actual questions and how we're going to use calculus to answer them. So we start off, we've got a position function here, which is t times t minus 3 all squared. So this is actually a cubic. And it describes the position of an object moving along a straight line. So this is not something that is being thrown into the air. This is, imagine something like a number line. So if we start here at 0 and we've got s of t, this is just moving back and forth, back and forth. Now you could graph this another way. So if this was an object, I'm just going to go ahead and draw an object there. If this was an object, what it's saying is the object is starting here, and then it's starting to move, and then maybe it shifts back again, and then shifts this way again, and then shifts back again, that sort of thing. So this equation is describing the motion of that object. You could, however, you could just graph the motion of the object as time goes forward. So rather than following the object as it moves back and forth on that line, you could also graph the motion of the object. So as it maybe starts off, it gets further away from the line, comes back, crosses the other way, etc. Now, I haven't put too much thought into what that graph will look like because I actually don't want to. We'll maybe come back to it at the end after we've because we can graph this. So after we've worked through the actual algebra and the calculus of this, maybe we'll come back and take a look at the graph of that. Now, if you were doing this question yourself, it might be a good idea for you to graph it first because that will give you some ideas. But I'm going to actually do it in that reverse order just for the sake of practicing here. Determine the velocity and acceleration at any time t. What that means is come up with an expression for the velocity and an expression for the acceleration. So we've got s of t is equal to t times t minus 3 all squared. So that means that v of t is equal to s prime of t. So I'm going to take the derivative of this. Now there are a few things you could do. You could expand this and simplify, and then you would just be taking the derivative of a polynomial. I'm just going to take the derivative in place here, and I'm going to apply a couple of rules. So I'm going to apply the product rule. So I'm going to treat the t like my first function and the t minus 3 all squared like my second function. So it's going to be the derivative of the first, which is just 1, the derivative of t, times times the second, which is t minus 3 all squared, plus the first, which is t, and now I'm actually going to have to use the chain rule to take the derivative of the second. So the derivative of the second is going to be 2 times the bracket without changing it, multiplied by the derivative of what's inside the bracket, which in this case it turns out fairly simple. It turns out just to be 1. So let me clean that up before I do anything further. So that's just t minus 3 all squared. And then that's going to be plus 2t times t minus 3. And at this point, again, I could expand things out and simplify it, or I could actually take a look and say, well, I've got a t minus 3 as a common factor here. And then when I take out that t minus 3, I'm left with a t minus 3 plus 2t is equal to t minus 3. And this one's going to be 3t minus 3. And just double check that I did that right. Factored out a t minus 3. This one just becomes a 1 times 2t. So, yep, that looks good. Now, you could have easily made the decision at this point. You might have said, no, I don't want to do it that way. I want to expand this out. So that becomes t squared minus 6t plus 9 plus 2t squared minus 6t, and that's equal to, let's see, 3t squared minus 12t plus 9. Now it's true, if you go this way, you're going to end up with a much easier time coming up with the acceleration expression. So you could make the argument this was a better choice, although you can see we're practically there this way as well. I could expand this out quite easily if I wanted to. So you know what? Since I've admitted that this actually ends up being an easier choice, I'm going to work from here. So my acceleration as a function of time is equal to v prime of t. So now I'm going to take the derivative of this very simple polynomial, and I end up with 6t minus 12. So there is part A. For part B, I've been asked to find the velocity and acceleration at t equal 4 seconds. So what that really means is I want to know what is v at 4 using function notation. And that is equal to, and I'm just going to replace this t with 4 minus 3, and then it's going to be 3, but again I'm going to replace that with a 4. And these are just these values of t right here that I've replaced. And so I end up with 1 in that first bracket. 3 times 4 is 12, minus 3 is 9, so I end up with 9. And for my acceleration at 4, I end up with 6. I'm just going to go ahead and make this replacement. I'm not going to change color. It's 12. So I get 24 minus 12, which is equal to 12. Now you do have to be careful here because we are talking about these quantities have units. So my answers are not complete yet. I have to actually talk about what the units are. So to understand that, you need to understand that S of t is in meters. And so V of t, because we took the derivative with respect to time, so we took the change in position, which was in meters, but we did that over the change in time, so that's meters per second. And then our acceleration, we took the change in position, which was meters per second, and we also did that one over time. So this one ends up being meters per second squared. So therefore, at t equal 4 seconds, velocity is 9 meters per second, and acceleration is 12 meters per second squared. And your answer is not done until you finish this with the correct units. Part C, describe the motion of the object after 4 seconds. So what is it doing after 4 seconds? So after 4 seconds, the speed is already positive, and it's accelerating. So that means it's moving away from us at an increasing rate, or it is moving, so the velocity is positive and the acceleration is positive. So therefore, the object is moving away, as in when I say away, I mean in the positive direction. At an increasing rate. And if we go back to that graph that I talked about, so that would be S of t is equal to t times t minus 3 all squared. A very quick sketch of this graph. There's my t, there's S of t. I'm going to have zeros at t equals 0 and at 3. And I'm going to do my interval table in my head. I know that at t equals 0, when t is equal to 1, well, this is always positive. So what's going to happen is this is going to go through here like a linear, and it's going to meet here like a quadratic. So it's going to look like that. And so to join those up, we end up with something like that. And now this part goes up and up and up. And so there you can see at t equals 4 seconds, it's not only is it moving away from the x-axis or the t-axis, but it's going to get steeper and steeper and steeper, which means it's going to get faster and faster and faster as it moves away. Now we've got an example that I've taken from a textbook, and it's a good example because this is one that comes up quite often. I gave a sample equation on a few pages ago talking about an object thrown in the air. It says a baseball is hit vertically upward. The position above the ground with respect to time is given by this equation. And it says here the position above the ground, and that tells us that up is positive. The equation tells us that up is positive as well, because you can see it has a y-intercept or an s-intercept that is here. Determine the maximum height. Now this is a quadratic. Technically, you could just go ahead and find the vertex of this quadratic, but that would defeat the purpose of what we're doing here. We're using a simple example, but I don't want you to go back to simple methods to do this. You can use those simple methods to verify your answer perhaps. So what does it mean if we throw something up in the air and it starts at 1? It's going to travel like that. But what do we know here? What do we know about the speed as it's going? Here it's going up and up and up, which means the speed is positive. Here it's coming down, 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 which means the speed is negative. So at this point, we know the speed has to be 0. Another way of thinking of that is to think of the tangent line. The slope of the tangent line is equal to 0. But that's the same thing as you can see, the instantaneous rate of change, which is the speed. So however you think about it, we end up at the same place, which is the first thing we're going to need is the derivative. So s prime of t is equal to negative 10t plus 30, taking the derivative just using the power rule for each of those terms. And then I'm going to set v of t equal to 0, and of course I want you to remember s prime of t is the same here as v of t. So I end up with v of t, negative 10t plus 30 equals 0, negative 10t equals negative 30, t equals positive 3. So that tells us that the vertex is at 3. But this is when it's at the maximum height. So to find the maximum height, I need to, I'm not using h, we're using s here. I need to find s of 3. I need to find the height at this time. So s of 3 is negative 5 times 3 squared plus 30 times 3 plus 1. 3 squared is 9, so that's negative 45, plus 90, plus 1, and that's equal to 46. So therefore, max height is 46 meters. Determine the velocity when it is caught 1 meter above the ground. So what it's saying here is that there's someone standing over here who catches it, hopefully not with their head, catches it when it's 1 meter above the ground. So what we have to do is we have to solve for when does that time occur? When is it 1 meter above the ground? Now we could solve for s of t equal to 1, or we could recognize that there is a symmetry here. Because it was thrown from a height of 1, then and it took 3 seconds to get to the maximum, for it to come back to a height of 1 is also going to take 3 seconds. So we actually know that that occurs at t equals 6. So now all we need to do is find v at 6. It wants to know what is the velocity when it's caught 1 meter above the ground. So if it's caught at t equals 6, then v of 6, we go back to our s prime, which is negative 10 times 6 plus 30, which is equal to negative 60 plus 30, which is equal to negative 30. Notice that I'm not working with any units here. My units are all consistent. I've checked that. I know that. So therefore, it is caught traveling 30 meters per second down. So I notice how I took that negative and I changed it into a positive because I specified the direction this way. You could also have said it is caught traveling negative 30 meters per second, but I think that's a fairly crude way of actually expressing it. And that's it for this lesson. You might also want to, I strongly suggest as a matter of fact, that you review the need to know information on page 126 and then plenty of practice problems to take a look at.